Welcome back. So today's lesson is on geologic time, your chapter 8. Last time, the last several lectures, we'd been talking about plate tectonics, the expression of plate tectonics through our earthquakes, the seismic activity, the volcanism, so our volcanoes and our mountain building. We also talked a little bit about several structural geologic deformations. So first off here, I do want to kind of take us through a cross section through Arkansas and take a look at some of those names of those structural deformations that are in Arkansas. So let me switch real quick to our handy map of Arkansas here. And so in looking at our geographic kind of stratigraphic provinces, these little sections that we divide up the state by, they are going according to what's going on with the geology in the rock bed. And so I'm going to do a little cross section for you. I have a drawing. I don't know, maybe you want to draw it. But I want to take a look. I'm going to start in the Ozark Mountains province and work my way down through the Arkansas River Valley, the Ouachita Mountain region, as well as the Gulf Coastal Plain. So pretty much I'm going starting the north of the state on the west half here of the state and making a cross section down and through the kind of west half of the state. And so some of the cities that are on here, Hot Springs and such, I have a few of those cities listed on my little drawing that I've made for you. Another way to look at this, doesn't have all the cities on it, but we will be taking a look at Arkansas through geologic history at the end of our lesson. And so this is more or less showing kind of the rocks and the ages of the rocks, and we'll take a look at that again a little later. But as you can see, we're kind of looking at the cross section of what's happening with the rock layers. And you can notice here we're having quite a bit of little deformation happening. I did mention that the Ouachita Mountain region really did structurally get deformed. If you recall the formation of Pangea, all lands coming together, and then the splitting apart of Pangea, so Arkansas through geologic time. And then the Arkansas River Valley, not quite as deformed. It's kind of a transition zone between the Ouachita and then the Ozark Mountain, the uplift that created that dome there. So a little bit of a picture there. Then I do have my drawing. Don't know that I can get it all on at the same time. We'll get a portion of it. So I'm starting at the north, okay? Gotta orient yourself there. The north part of the state in that Ozark Mountain region. Of course, Missouri would be to the north of us. And then this is all Arkansas. So way there, up there in near Harrison would be a city on your map that has the cities on it. This is part of that Ozark dome. So we did talk about the domes and the basins. So that upward but circular compression that lifted up a dome. So the Ozark Dome. And then on about around Clarksville on your map, we start to get some what we call normal faults. And so these are those normal dip slip faults where the hanging wall moves down. If you remember that, normal faults, okay? And then once you start to get to the Morrilton area, remember Morrilton was a great place to see an anticline. So it's a series of the anticline, which is the upward arch, and the syncline, which is the downward arching features. Again, compression forming both of those, okay? But not too severe of deformation, but anticline, synclines, okay? And those were types of our folds, our two main folds in there. Then along about the Ouachita Mountains region, this is a very highly deformed area. When Pangea was assembling, so North America, South America, and even Africa, all the land coming together, and from all that compressional forces in there, we're really getting a lot of the anticline, syncline folding to the point that we're actually getting what we call the thrust faults, which are those reverse dip-slip faults. So extreme kind of compression happening to create those. And that'd be along about the hot springs area. I have a couple features in here where we did talk about our volcanoes, where we had a couple episodes in there of volcanism that we mentioned. So here's Little Rock, here's Murfreesboro. And so we have this batholith. Remember that intrusive magma that solidified, massive rock body there. So intrusive igneous batholith, which is they call Granite Mountain, but we know better, it's syenite. If you remember that, the syenite batholith. Okay, so there along about Little Rock for that. And then the explosive volcanic eruption of the crater of diamonds that brought the diamonds up, right? So that would be around Murfreesboro, the crater of Diamond State Park in that area. And then, as you notice here towards the Gulf coastal plains, it flattens out, so the terrain does flatten out, and we do have quite a bit of the clays, gravels. So this is more getting runoff from some of the river region, but it's called a Gulf coastal plain. Kind of in the El Dorado would be towards the southern part of our state, where this is where the Gulf of Mexico actually did extend up to. And so right now the Gulf of Mexico is way down there by Texas, Louisiana, borders there. But in its geologic past, the Gulf was way up here in Arkansas. So we're getting clay, sands, and gravels. And if you recall, this is also where we got those lignite deposits, the coal deposits. Not a very high carbon content of coal, but that is where that indicated to us that we had a swampy coastal kind of a region in there to get those lignite or coal deposits. So this is sort of a little cross section of Arkansas. Yeah, just kind of taking us on to, and then Louisiana would be below us there, so this would be southern Arkansas region. But many of those terms we heard of through plate tectonics, earthquakes, mountain building, and our volcano lessons. So I'm trying to kind of summarize that in what we see in the bedrock in Arkansas. So a nice little cross section of Arkansas, of those stratigraphic provinces. Okay. So you have a couple resources on Blackboard. One, let me go out of this real quick, is a, if I can find it. There it is. Short history of historical geology. And so this has got many of the gentlemen are kind of the founders of what we call modern geology, our modern way of thinking about geology. So it's kind of starting prior to the 1600s and recognizing here that it really wasn't in the 1600s realized that the Earth had an extremely long history. It was thought maybe just a few thousand, 100,000 years or something. Well, not even that, maybe about 4,000 years or so. So that it really did not have a long, immense, or deep time of a geologic kind of a past. But now we do recognize that the Earth has an extremely long geologic history, on the order of 4.6 billion, with a B, billion years, a 4.6 billion year history. And so prior to that, we just did not have that understanding. So this does introduce several names in here as you go through Nicholas Steno, and we may go a little out of order as what's on this, but this is a good resource for you to give you a little more background on some of these gentlemen and principles that we're going to be talking about. So there's that for you on Blackboard. And there is another document on Blackboard that we will take you through when we talk about the history of Arkansas through geologic time. Let me pop that under the screen real quick so you can look for that. And it might be nice to have that handy as we do go through each figure towards the end here, but several figures with some drawings, okay, of Arkansas, okay, at various geologic time periods. So there's 4 on the front, and there's 4 other figures on the back. So 8 figures in total of various time periods. Okay, so you'll want to maybe have that handy as we do talk about Arkansas through geologic history, and that comes kind of towards the end. So you might want to go grab that, make sure you do have that handy. But starting us off, okay, we kind of some historical notes, kind of what I like to do as well on that. But the idea that landscapes, so our mountains, our volcanoes, all these things were through catastrophes that developed that these weren't just a natural process that was going on. Something catastrophic had to happen to form those. Our first gentleman here, and I'll try to write some of their names down. James Usher. Maybe make sure to go back and look at these. Okay. An archbishop. His idea, kind of in the mid-1600s here, he used the Christian Judeo Bible, the book of Genesis, to retrace Adam and Eve's kind of lineage, history in that, and come up with the idea that the earth was only a few thousand years old. He believed earth was created in 4004 BC. I mean, he had it down to the day, the time, and that sort of thing, what he was able to gather from the Bible. So, we're talking maybe 6,000 years, was his best estimate using the Old Testament, the Bible, for this. So, historically, he's kind of one that's beginning to think about, well, how Earth was created, when was Earth created, sort of thing. He's like the early one that begins to think about these things. Then we have a gentleman, Abraham Werner, and he's called a Neptunist. Neptunists were sort of, there were like 2 schools of thought on Earth history, and Abraham Werner was kind of leading up the Neptunists. So Abraham Werner. Okay, a Neptunist. Neptune, so Neptune's the god of the sea, right? So his idea was that all of the rocks on the earth precipitated out, crystallized out of this universal ocean that covered the planet in its past. And so then this idea of our rock cycle, he didn't use that. He just thought that, all the crystallized, kind of like the igneous rocks, metamorphic rocks, all of these crystallized out of universal ocean was his idea. So there's that one school of thought trying to describe the rocks, the land, the geology of our planet, So Werner came up with that with his teachings, the universal ocean, and that these rocks just kind of precipitated out from that. And then this other kind of school of thought came from James Hutton. We've heard about James Hutton before. It's two T's. Hutton was a Plutonist. A Plutonist, they called him, or a Vulcanist. And so, if you recall, James Hutton actually created the rock cycle that we studied earlier in the semester, where you went through the igneous rocks, right, coming from the fires within the molten magma, and then the sedimentary rocks through the weathering process, lithification, you know, remember that, and then the metamorphic through additional heat pressure, you can get metamorphosed rocks. So he came up with the rock cycle. James Hutton did, and he's also known as our founder of modern geology. So that was his kind of school of thought, and then we had, you know, the Neptunists with their school of thought, sort of two competing ideas at the time. Kind of now we're in the 1700s for this. He also, if you remember, come up with that quote there: "The present is the key to the past," where we can look at sort of the present and interpret the past from the geology, from the rocks. And so uniformitarianism is what that's formally called. Uniformitarianism, a long name there, but it is a fundamental principle of geology, one of the very important principles of geology, in which it talks about the laws of biology, chemistry, all those processes that are occurring on our planet today, in the present, also occurred in the geologic past, is the premise of our principle of geology known as uniformitarianism. So the present is the key to the past. And he wrote of that in the Theory of the Earth in 1795. It's kind of like they all have their little book or several books that they wrote. The Theory of the Earth, 1795. And in which he did state that we see no vestige of a beginning and no prospect of an end. And so his idea here is talking about deep time, that the Earth is extremely long history. So again, we're now we know 4.6 billion years, but at that time, at this time, that idea, that concept of deep time, talking billions of years, it just did not enter the minds of people. And so he was realizing that we really don't see any vestige of a beginning, and we don't see any prospect of this ending. So this concept of deep time comes from James Hutton. So we kind of had these two schools, the Neptunists and the Plutonists, and eventually the Plutonists did win out in there. What happened was with the Neptunists, Abraham Werner's students actually were the ones that refuted his idea of a universal ocean creating all of the rocks. They were studying, he had a group of students that were out studying volcanoes, volcanism. And he taught that if you had some sort of fire within, that had to have come from some sort of coal being burned beneath the Earth's surface. So he didn't have this idea that Hutton had with the molten magma. He thought, well, those were coal beds generating those volcanoes. Well, his own students went out and surveyed, and they're like, there are no coal beds in this area that they were studying. And so they pretty much refuted their own professors' work, that it couldn't be possible that there were this heat, this molten material, the lavas, were coming from within the Earth itself. And then rocks were being formed as they cooled from the lava. So yeah, his own students refuted that. So the Plutonists, the Vulcanists did win out eventually there. So James Hutton does become sort of our father of modern geology and that doctrine of uniformitarianism in his very important work, Theory of the Earth. So the present is the key to the past is something that does relate to uniformitarianism. This idea that the biological, chemical laws, physical processes that we see today have operated in the geologic past as well. Okay. We also go along here about the 1800s, and we're introducing here Charles Lyell. Now his main training was as a lawyer, so he was very eloquent in his speaking, could really make his case very well, and he began working kind of with and along James Hutton's work, this idea of uniformitarianism, and he was really able to eloquently express that idea. And so he, of course, wrote his book, The Principles of Geology, where he really does lay out that idea, that concept of uniformitarianism as well. Okay, but initially it was James Hutton that first spoke of it, but Charles Lyell kind of popularized it and made it a little more understandable for people. Now, Charles Lyell, interestingly, was a mentor of Charles Darwin. So maybe you've heard of Charles Darwin. Let's write Charles Lyell up first. You're thinking, well, what does Charles Darwin have to do with anything about geology? Well, Charles Darwin actually started out as a geologist, studying geologist. As a young man, you know, his father's like, you got to do something with your life. And Charles Darwin, he was like, well, I certainly don't want to be a doctor like his father was. He actually witnessed, as a child, he witnessed a person getting their leg amputated without any anesthesia, so that traumatized him, and he definitely did not want to be a doctor. So he's like, okay, I'll do geology. He became a minister and collected beetles and different things. But he was invited to go on a voyage on the MS Beagle expedition kind of thing around the world, sort of voyage. Ended up taking 5 years to complete that voyage. But what he was doing, he was writing to Charles Lyell and sending some samples of the geology, taking lots of detailed notes of the geology as he did make this voyage. This 5-year voyage kind of culminated in his notes. And Charles Lyell was like, hey, you need to kind of work with me when you get back. But what Charles Darwin kind of fell in love with also was the biology. So he was noticing that the evolution, there was an evolution of biological life right alongside the evolution of the geology of the land. So the land and living organisms sort of evolved together. And so that trip kind of culminated with the theory of evolution of species by natural selection, which is Charles Darwin's very famous paper, theory of evolution by Charles Darwin. So he kind of went the way of biology, much to the dismay of Charles Lyell, who really wanted to snag him for the geology side of things. But Darwin kind of had his own thing, and he was going to go and do the theory of natural selection in there. Okay, evolution is Charles Darwin's kind of contribution, but he did the biology side of things. But really that life had a very long history as well, right alongside our land too. So, okay, and so we've got another law here that we talk about, So some of these are called principles, and some of these are called laws of geology. But notice up here that it says relative dating. And so we use these principles, these laws of geology, to piece together a sequence of events. And so that's called relative age dating. Kind of interpreting a sequence of events and putting them in order. What happened first? What happened second? What happened third? And so on, of a sequence of geologic events. And so these laws and principles go towards helping us have that understanding. So this one here called the law of superposition. This is developed by Nicholas Steno. So Nicholas Steno. Steno was, and this is kind of in the 1600s, late 1600s, 1669, was an anatomist. And he used to do a lot of dissections where, like he had an audience in a big theater, like where people would watch him do dissections. And he kind of was one, we'll talk about it a little bit later when we talk about kind of our inclusions, but he was the first to kind of understand that there were shark teeth inside of a rock. This idea of fossils kind of was his contribution. But this law of superposition, he was noticing that, and it seems obvious to us now, but until he really kind of spelled it out, it wasn't widely accepted, but that in an undeformed sequence of sedimentary rocks, so or layered igneous rocks, but something that had layers. So we've got our sedimentary layers. Maybe we've got a little sandstone, a little shale, something like that, but layers of sedimentary rock. The rocks at the bottom of that layer are the oldest. Those would have been the first ones to deposit out. And then the next one, a little bit younger, a little bit younger, a little bit younger. And so those that are at the very top are the youngest layers, the youngest event then. And so this superposition, okay, the oldest rocks are at the very bottom, the youngest rocks are at the top. And that seems like just a simple little thing, but until he really explained that, it wasn't widely accepted, and it really helps us relative age date an outcrop of rocks. So you can look at, okay, that lowest layer, that was the first depositional event, and then the next layer, and then the next, and then the youngest would have been the top layer. That is the law of superposition. And so this is accredited to Nicholas Steno. Okay. And we do see this in the Grand Canyon. It is very well illustrated in the Grand Canyon. So here's like a live picture of the Grand Canyon, looking at all the layers in there. Okay, huge layers. Okay. We're talking millions of years of geologic history in those rock layers. Okay, but the superposition, your oldest event would have been way down here, the Supai group, the Hermit Shale. So this is a shale bedrock. Here we have some sandstone, sedimentary rocks, the Toroweap Formation, the Kaibab limestone. So here's the limestone. Remember the chemical sedimentary rocks. And so oldest event, next to youngest event. So it does get younger as you go up, okay, in layers. That's known as superposition. There's an American geologist, John Wesley Powell, who was the first to actually make a boat trip, right, through the Grand Canyon. And in his little book that he wrote, he talked of the superposition of those layers and how those layers, each layer had a story to tell. It's kind of like the book of Revelations in the Grand Canyon, because it was telling a geologic story as you went back in time here, the lowest layer, the oldest event, and went forward. and it could tell us something about their depositional environments. You know, for say a shale, what do we got going on? A sandstone environment, the limestone environment, so oceans and things like that. So yeah, an early kind of American geologist, and he made the first successful trip through the Grand Canyon by boat. He did, and so there's an American for you thrown in. But yeah, this really does illustrate the superposition, very important law. Besides uniformitarianism, superposition is another principle or law of geology. Here's another one. Principle of original horizontality. Again, this seems like common sense, but until it really got spelled out, it wasn't widely accepted. But horizontal originally. So rock layers, okay, will typically be laid down or deposited in a horizontal fashion, okay, in a horizontal fashion. So if we see an outcrop of some tilted strata, all the layers kind of tilted, or the ones where we see the anticlines and the synclines, the folds, okay, or the faulting, that kind of thing. Something had happened. That event had to have happened later, because rocks are usually, typically, originally horizontal. So layers of sediment are generally deposited in that horizontal position. Rock layers that are flat have not been disturbed. So we know there was no disturbing. But if you get the folding happening, the synclines, the anticlines, we know that that event happened at a later time, okay, because they're originally horizontally laid down. That's the principle of original horizontality. And I think there was an interesting picture, kind of a nice one, of really that folding of the rocks. Okay. Let's see, this is page 253 in your book. Of the 8th edition of your book. Okay. So originally these layers were all horizontal, and now you're seeing, okay, the undulation, the anticline and the synclines that occurred from compression. So that event, that geological event, should have happened sometime after their original deposition. So they were originally horizontal, and then some sort of compression happened on the rock beds to create those folds, those anticlines and those synclines in there. Okay, so these principles all together, I know we're taking them one at a time, but these principles all together help us build up that relative age dating. Which event happened first, then what happened, then what happened, okay? Gives us an ordering of a geologic sequence of events. Okay, so that's the principle of original horizontality. The next one, the principle of cross-cutting relationships. Okay, this is a very important one because, so you've got your original horizontal, position of your rocks, and then should you get some sort of cross-cutting that happens, and a cross-cut could be from faulting. So say you've got all your layers built up here, and then you get some sort of faulting happen. Remember, you've got that break, and then you've got motion. So a fault could have happened. Or you can get some sort of an igneous intrusion, right? So we've kind of talked, and I think I've given you a picture before of this, but here's another one here. So I've got a rock here that was originally there, and then this intrusion, this igneous intrusion. So that hot kind of magma working its way through, cross-cutting through the rock. Well, this rock, the black part of the rock, had to be there first in order to get cross-cut. So we know that the black rock was the first event. It was deposited first, it's older, and then the intrusion happened. So that pink part there, the granite intrusion, happened second. Okay, so that's a cross-cutting principle. We can figure out the relative ages, the relative dates here, the order of the events. So the black rock first, then the intrusion, because the rock had to be there before the intrusion could happen to affect it. Same thing when you get a faulting. Those rock layers have to be there in order to get cut and motion to take place along the fault line. So cross-cutting principle helps us kind of set up a relative age dating in there. Here's a nice little picture representing some of those cross-cutting relationships. So here's a fault. So I was talking about faulting. So all these kind of color-coded here layers. So that layer and that layer was the same rock layer at one time. That pinky one there, a little lighter tan. Here's a sandstone layer and a yellow layer. At one time, those layers were all together. Okay, and then there was movement along a fault line. Okay, so these layers were deposited, originally horizontal, okay, and then the fault occurred. So again, we're setting up an order, a sequence of events, okay. On this one, here we have a dike, so an igneous type of intrusion. Remember our dikes? So it's going all the way up through that very top layer. So this is a much more recent event. All of those rock layers had to have been deposited first in order to be cross-cut by this dike here. So the dike is a very late event. This layer down here, this sort of tannish layer, that would have been the first event, the first rock layer. So that's the oldest event, okay? And then this would be like the youngest event. That igneous intrusion would have been coming more recently. Okay, so we're putting together superposition, original horizontality, and cross-cutting relationships to order a sequence of geologic events. And so that's kind of what we can do to use these principles or these laws of geology in relative age dating. Inclusions. So inclusions is where you get a piece of rock that gets enclosed in another rock. It's not necessarily just a rock, but it is that as well. But Nicholas Steno, as I mentioned, where'd he go? Nicholas Steno was one that he did a lot of dissections, as I mentioned, and he was dissecting a great white shark, and he had a big audience watching him do that. But he got to thinking, as he was looking at the teeth of the, where'd he go? Of the sharks. Okay, he remembered and recalled that these little things they used to call, okay, it was a rock, okay, that had this little tongue-looking object inside of it. Okay, a tungstone is what they used to call those. And he got to thinking, those tungstones sure do look like shark's teeth. And so that got to him to thinking that that's actually a shark's tooth that got included inside of the rock. So sediment went in and compacted around that shark's tooth. And so it wasn't that it was just always like that. That's just what they thought. That's like, oh, those have always been around. That's just how they were. And that's how they look. But he got him to thinking, when he did that dissection, that that's actually a fossil of a shark's tooth, fossilized shark's tooth. So this idea of a fossil being an inclusion inside of another rock. I actually have a very large shark's tooth here. But these tungstones, so these stones that just had shark's teeth in it, you could probably see that from there. That would have been a very large shark that this one came from. But here's another one that's been kind of permineralized, and it's black in color. But the shark's teeth, we put them up under there as well. are inclusions, okay, within a rock. So that kind of idea of a fossil. There's actually been some found in Malvern, Arkansas. Here in Arkansas, there's some tiny ones here. Shark's teeth. And you're thinking, sharks in Arkansas? What? Well, as I've been mentioning, Arkansas was a very different landform in the geologic past. And so these are from Malvern, Arkansas, from the Cenozoic. We'll go through our time periods pretty soon. Cenozoic, okay, time period. But Arkansas had seaways where sharks did live, and so the shark's teeth have gotten included into the rock bed of the sedimentary rock, and so yeah, you can go and you can find fossils of shark's teeth in Arkansas. Okay, so again, it tells us something about past environments when we can get those, but this idea of fossils got Steno kind of to thinking. So he was the first to correctly identify shark teeth kind of fossils in rocks. Okay, and they just thought, well, that's called a tungstone, and that's how it's always been. But so this idea of inclusions can tell us something, again, about a sequence of events. And so in this tungstone or shark tooth fossil scenario, the shark would have been the older kind of event. So the shark lived, he lost his teeth, right? And then sediment built up around it. So the rock, probably a sandstone of some sort or a shale, sedimentary rock, accumulated around it and included the shark tooth inside of it. So the rock containing the inclusion is younger. So the shark lived, lost his teeth, and then the rock formed. So the rock containing the inclusion is younger. I also have some shells and various things inside the rock. So these little shell organisms that secrete shells, were living first, and then they died, and then the sandstone included them in it. And so that's an inclusion. So for example, let's just talk about rock layers rather than fossils. Let's say we had a sandstone layer in contact with some granite, and there's little pieces of granite inside the sandstone layer. Well, which rock is older? Okay, so because there's little pieces of granite included in the sandstone, that tells you that the granite is older. The granite was there first, kind of got eroded away to broken down into some little pieces, and then the sandstone layer was deposited on top of that. So the sandstone's younger, the granite is older. So the rock that is containing the inclusions, granite, is younger. So your granite's older and your sandstone's younger in that example. Again, helping us have an understanding of age dating. Relative age dating is what that's called. A sequence of events. So principles of inclusion in our little Steno with his shark tooth. And this idea of a fossil was kind of getting started in Nicholas Steno's mind. Okay. Now, we're talking about some of these unconformities they're going to take us through. Let me see if I think I passed that. An unconformity. There's 3 types of unconformities. But an unconformity is a break in the rock record. So what could happen is like a gap in the rock record. There could have been an erosional event where a lot of erosion took several layers of the rock bed and moved it on down the line. So now there's a gap, okay, in the rock record. Or you could get just a long period of non-deposition. of rocks. But in some way, there's a gap in there. So either through non-deposition or erosion. But there's some layers in there that we just have no record of. Either they got all eroded away or there was just a long period of non-deposition. So we do talk about these unconformities. There's 3 types. One is called this angular unconformity. So this is where you're going to have, and now remember, I've got some this is a limestone layer that's tilted. Remember that limestone would have been deposited in a horizontal fashion originally. Remember our original horizontality principle of geology? So that would have been originally horizontal. And then they got tilted. So uplift, regional uplift could have occurred where you're getting a little compression happening, maybe getting some tilting going on. So something in the compressional forces causing that to tilt a little bit. So now we've got it kind of at an angle, all those layers. Then sometime later, you're going to get probably a subduction beneath the ocean environment where you can get resuming of deposition. So more sandstone began depositing on top of that angled limestone. And so here what we talk about, here's kind of where the break was. So there was erosion that occurred after that got tilted, the limestone got tilted. And then we had resuming of deposition. So submersion, redepositing occurring, getting our sandstone layer. So here you end up with a tilted layer, okay, beneath a flat lying layer of strata, coming in at an angle like this. And so that's the word there that they use, angular unconformity. So tilted rocks that are overlain by a more flat lying rock body. Okay, and that's a nice example of an angular unconformity. Here's one we call a disconformity. And so you've got parallel strata, okay? They're nice and horizontal, but on either side of the unconformity. So there was a break in deposition or an erosional event that took some of the layers away, and then you had resuming of deposition. So a little gap kind of in the rock record, and then deposition. A gap in the rock record, and then resuming of deposition. And so it's just essentially 2 parallel layers of strata, okay, separated by that gap in the rock record. So on the unconformity we call that. But 2 parallel layers, okay. Disconformity. Then one called a nonconformity. Now the nonconformity is when you have some sort of igneous material, or it could be metamorphic, but it's an older event. So here we have granite, which is an igneous rock, if you recall that. So here we have the granite, and then it's overlain by the younger sedimentary strata. So we've got some sandstone in this one. Okay, so here we had an episode where the granite was being deposited out, okay, and then that line there, kind of that wavy line, was some erosional event. Okay, so it took away a few layers in there. We really don't know how many layers were removed, but we know that it's an unconformable surface, so non-deposition or erosion occurred. And then resuming of deposition of the younger sedimentary strata. So older igneous or metamorphic below the unconformity, and above the unconformity, a sedimentary strata, younger sedimentary strata. That is what we call a non-conformity. So metamorphic or igneous rocks in contact with sedimentary strata. So the younger is the sedimentary strata, and that's a non-conformity. Okay. More flat-lying, non-conformity in there. Okay, the Grand Canyon is an excellent example. It shows all three of these unconformities. So right here we have a nonconformity in the Grand Canyon. So here you've got granite, right? You have some waviness here of metamorphic schist. Remember our metamorphic rock schist? So that wavy stuff there. So that's metamorphic rock down here. And then you've got the gap, so the red line there. And then you've got your sandstone, your sedimentary, this whole thing's the sandstone right here. That's a good example of the nonconformity exhibited in the Grand Canyon. Here you have the angular unconformity. So here you've got this layer here coming in at an angle, okay, with more flat-lying strata over the top, okay, the shale above that. So right along there, you've got an angular unconformity. Up in here, so we've got some limestone here, and then you see that line there. That's the gap in the rock record, the unconformity. And then deposition resumed, and here we've got some more limestone layers here, but they're essentially parallel to one another on either side of that unconformable surface there, that red line. We call that a disconformity. So all three of these unconformable surfaces, gaps in the rock record, we call that, are exhibited in the Grand Canyon. It's an excellent example of this. Okay, fossil evidence, so past life. So yeah, I got Steno kind of thinking about past life. And so fossils, they are traces or remains of once living organisms, so prehistoric kind of life that gets preserved in our rock record. And so they're generally found in sedimentary rock. Occasionally you'll get it in a metamorphic or igneous, but because of the heat type involved, it's kind of hard for those to survive. Never in igneous, but mostly going to be in our sedimentary rocks. And I believe we did mention this when we were talking about the sedimentary rock unit of our rocks back in chapter 2. So the study of fossils or past living organisms through geologic time is known as paleontology, so the study of past life, so study of fossils. And we have a gentleman, George Cuvier, let me see, who is a paleontologist. Read his name out. Oh, let's see, I'm hoping you can still see here. George Cuvier, French zoologist. He's known as our kind of the father of paleontology. He was the first to come up with incontrovertible evidence of extinction. It just never entered our minds until he spelled it out that there were living organisms on this planet that are no longer. They are extinct, and extinction is forever. They don't come back. And so he was studying elephants. He was French. He was there in Paris, kind of studying some elephant fossils there, studying in Africa and India. And he was noticing that there were, differences that we no longer see elephants today that look like these elephants in these fossils that he found. And so the woolly mammoth and things like this. And so this got him to thinking that there were organisms that lived on this planet that are no longer living here. So everything that's on the planet has not always been here. So he was the father of paleontology, we call him. But yes, his incontrovertible evidence that said, yes, there have been extinctions on our planet. So that's George Cuvier's kind of contribution, father of paleontology. Okay. So, and we mentioned fossils when we did talk about the sedimentary rocks, but they're very important because they aid in the interpretation of the geologic past. And so learning something about past environments can help us. I think way back in the beginning I showed you that limestone that had the rugose coral in it from northern Arkansas. And so what we know about coral today is that they need warm, shallow seaways, kind of clear water, warmer temperatures, and seawater. So this told us that northern Arkansas at one time in the geologic past was below an ocean, and so can tell you something about past environments. So they are very important in helping us understand the geologic past and interpret that. Serve as important time indicators. So we're going to see that our fossil kind of assemblages can tell us, again, it's relative age dating, can tell us what time periods, what geologic time periods a particular rock is associated with. And so it can really aid as a time indicator. And we'll see that here in a bit. But allow for correlation of rocks from different places. So correlating rocks, matching up rocks in one location with rocks in another location, and getting their time frame too can tell us, you know, this event occurred in this region during this time period, because we can match up rocks here with another location because they had the same fossil kind of assemblages. So these fossils, ordering of the fossils in the rock layers is something that we do use, this principle of fossil succession. They'll talk about here in just a bit. But let's look at some fossils, the conditions that you're going to get fossils out of. So favoring preservation. One thing is you need some sort of rapid burial of that organism so that it doesn't decay, you know, with oxygen being exposed to it. So some sort of rapid burial. And it does need to have hard parts. For the most part, there are some soft-bodied ones that get stuck in amber or sap from trees we'll look at. But possession of hard parts. So you need skeleton, you need teeth, you need some sort of a hard part. Shells, I kind of was showing you some shells. The organisms secrete shells. So some kind of a hard part. So something like a worm. Okay, yeah, it's varied, that's one part of it, but a worm doesn't have the hard parts, and so a worm would not make a good fossil candidate for preservation because it doesn't have the hard parts. So these are some good things that would help us to preserve a fossil. Here's several pictures. I actually do have the actual samples of several things, but I'll kind of show you my samples and talk about each of these ways of getting a fossil. Some of them are just little carbonation kind of imprint sort of things. Here's the one with the amber, and we'll talk about that one right there. But let me find mine and try to share those with you as well. Here I have some petrified wood from Arizona. Beautiful colorations on these. Dated from 220 million years ago. This is a what we would call permineralization. So it was once wood, right? So it's a petrified wood, but solution, you know, with lots of minerals in it, crystallized out in the cracks and crevices and actually changed that over to the rocky material. So per kind of mineralization, getting some beautiful coloration out of that as well. So permineralization is a way that we get petrified wood. Another way we can get it are through these molds and casts, they call them, and I have some of my little trilobites here. Let's see. Little trilobites. So permineralization there, and then this one. Now this isn't actually a real one there, but this one is where you're seeing the casts and the mold of the organism. So the trilobites, they're like my favorite little fossil. Here's the trilobites, and so the trilobites had 3 lobes, so trilobes in them, and so they're getting a little mold and cast out of these. This is just a replica of what a real one would look like. But some of these could get, you know, like a foot long, and they lived in the ocean, so there were marine organisms, and they scurried kind of along the bottom of the ocean. But these are good examples of a mold or a cast in there. Carbonization, let's see if I can find that one. Here it is. Here I have some fish. Okay. So some impressions and carbonization. See if we can make that out on here very well. I don't know how well that's going to show up, but here's a nice little, you can see the fish. They're all just kind of scattered. Here's a nice one as well. Impressions and carbonization. Head of a fish is just a bunch of them that got, you know, preserved into the rock there. So carbonization, fish impressions. The amber, so I don't have a little organism in my amber, but from tree sap that hardens. But you could get some soft-bodied fossils. The one they showed in your PowerPoint was a spider. But anything that got encompassed in the sap of the tree, and then that resin hardened into the amber, we call that, you could get some fossils of some soft-bodied organisms, but that would be some amber, okay? That would be one way to get a soft-bodied organism in there. Remember how those don't ordinarily fossilize well because they don't have the hard body parts. And then trace fossils. So you could actually get little tracks and trails of our organisms. I have one here that is from the trilobites. So I mentioned how those little trilobites do scurry along the ocean floor, right? And so I don't know how well those are going to show up, but there are little kind of scratch marks, okay, on that. That were made by our little trilobites. So that little scratch mark there as they scurried along and were doing their thing out on the ocean floor. And so those are some trilobite trails, okay? Other things that we see are something called a coprolite. So fossilized poo, excrement from the organism. So I have a little fossilized, oh, I don't know if I can get the lid off of that. Coprolite. Oh, I don't think I can get the lid off of that. But here's some. So it could be that it was stomach contents. It could be that it was waste material there. But we call that a coprolite, something of the stomach contents or the intestinal contents. So in a way, that's called a trace fossil. Another trace fossil I've mentioned was in our study of the dinosaur track that got left in southwest Arkansas, if you remember that, near the gypsum deposit. So that 3-toed trace fossil, because it was the footprint. Okay, it wasn't the organism itself. I don't know if that's going to show up very well either. May not. If there's anything at all for it. but I've got the three kind of toed, okay, prong there of the dinosaur is not really showing up very well. But again, footprints, that sort of thing, is a trace fossil. So it's not the organism itself, but it can tell us a lot about the organism. Did they travel in packs? You know, what was their environment? Scurrying along the bottom of the ocean? What were their stomach contents? So we could tell a lot about that as well from these so-called trace fossils. Okay. So yes, again, the permineralization, petrified wood, the casts and the molds. So that's a nice trilobite example as well. Here's a little carbonization. So here is a bee, but it's the carbon print of it. So the bees are pretty soft bodied, so they're not going to leave behind a good candidate for a fossil, but here it is, the carbonization of it. Here's a nice imprint of the fish, so carbonization and imprints. Here's the amber that has a soft-bodied spider that got fossilized. So sometimes we get lucky with the soft-bodied organisms. And here's some of that coprolite, so fossilized poo, which can tell you something about the trace kind of fossils there. Okay, so these were evidence of past life. That's our fossils will tell us this. And here's a dinosaur footprint in limestone. Looks like a three-toed dinosaur in that one as well. So a trace, kind of a fossil. Okay, so we talked about the correlation, matching up of the rocks from one region to another. And that is known as correlation. You're going to match them up of similar ages from different regions. So they could be really completely different areas, but you could match them up. And what they're doing, they're really relying on the fossil assemblage. What fossils are in those rocks? You see them in one place, that same assemblage, and you see it in another place, those same fossils. So you can match those up and say, well, these events occurred at a similar time. Okay, and so William Smith, another gentleman we're going to be adding to this, in the late 1700s. He was a canal builder, and so he was digging through rock to build his canals, and yeah, so he was up close and personal with the rock layers, the bedrock, and he was starting to notice the fossils in the rocks. And so, yeah, he noted that sedimentary strata in widely separated areas could be identified and then correlated, kind of matched, by their distinctive fossil content. So this fossil succession was the kind of really pretty much attributed to William Smith. So let me kind of start up over here with more people to talk about. Another one, William Smith. Don't want to leave him off of our list because he's very important. Okay, so this principle of fossil succession, fossil or faunal, because it could also be plants, not just animal, but fossil succession. They succeed one another in a definite and determinable order, and therefore any time period can be recognized by its fossil content. So depending on what fossils you have in there, these fossils do live for a certain amount of time and then they go extinct, right? That idea of extinction. Where'd our guy go for that? Cuvier, George Cuvier, and are extincted. So you have fossils, they're living their lives, and these can be, you know, fairly long geologic time spans. Others are a little shorter time spans, and those actually end up being very helpful index fossils that we talk about. And then they go extinct. You no longer see them in the rock record. Okay, so you can put an age to your rock according to which fossils are in it. So William Smith, this principle of fossil succession, this determinable and definite order that the fossils are in your rock units, okay? He helped us with that, William Smith did. But like I said, some of these fossils are a little more useful than others, and they call those index fossils. For a fossil to be good in helping us with relative age dating, it needs to be widespread geographically, so geographically widespread, but that its lifespan is a shorter duration, okay? So something like an algae, let's say, would not make a good index fossil because algae, I mean, we have algae today, and so algae wouldn't be the best for that. But something that is limited to a short span of geologic time, those become very useful in correlating and doing the correlation of the rock layers. So trying to match up rocks of similar ages in different regions by the fossil assemblages in them. So these index fossils, and a very important method for matching up rocks. So here is a nice example. We've got this rock layer here, kind of that pink layer. We're calling that the age of rock A. And this blue layer here, that's going to be our unit B. And off over here, this is showing the fossil assemblage in rock B, and this is showing the fossil assemblage, so what fossils are in rock A. Okay, and then over here we have this age ranges of some of these fossils that we're looking at. There's my favorite, the trilobites, right? They're a really good index fossil because their geologic time span was pretty short, okay? So we do in rock B see the trilobites, okay? So we can kind of get this upper limit here for the age because after this time right here, you don't see the trilobites any longer. They went extinct, meaning forever, they're not coming back. And so that needs to see those in there. You've got a window of time that it helps you, and the more fossils you get, the better you're going to narrow down. This one has a really long age, so it's not as useful because see, rock B has it and rock A has it, so it might not be as useful. Its period is really long. This one too is in both of them. This one though, right here, looking like Tyrannosaurus Rex, can't get that out. Little shorter time spans. This would be a good one. You don't see that in rock B, and you see it in rock A. So right away, you got trilobites in this one, no trilobites. You got a dinosaur in this one, no dinosaur. So you can, okay, because of that determinable, predictable order of the fossils, okay, we can set up the ages, the relative age dating of our rocks, okay? And that's sort of that method of the overlapping kind of fossil ranges in there. We could set that up. So fossils are a relative age dating method that we can use. That's relative. We are not putting an exact numerical value on it, but we can say, okay, this rock with these fossils in it formed at this period of time, and these occurred at a later period of time because they have these fossils in it. So that idea of fossil succession that Will Smith really helped us with can be used as a relative age dating principle. And in fact, the entire geologic timescale was put together on these relative age dating principles that we've been talking about. The original horizontality, superposition, cross-cutting relations, and our fossils in here, succession of fossils. All of those relative age dating. It's all relative age dating. Now we're going to switch to dating with radioactivity. And so using this method, we were then able to put the exact numerical values to the ages of our rocks. Okay. So radioactivity. Now, way back when we started talking about our minerals, we had the little chemistry lesson, and we were talking about the atom. So we mentioned radioactivity. So these isotopes, if you recall, And the isotopes are just a variety of an element that has a little bit different number of neutrons in their nucleus. They've got the same number of protons, but they have a little bit different number of neutrons, which changes up their mass number. Okay, so their atomic number's the same, that's the number of the protons, but the number of neutrons vary, so their mass number changes. And some of them can be what we call spontaneously decaying, so they're radioactive. They're just unstable and will spontaneously decay. Call that radioactive. And we talk about having a parent isotope, okay, the one that's unstable, wants to decay, and a stable daughter product. Okay, so we got their parent, that's the isotope, and the daughter product is stable, but it's the resulting decay from the parent. So you could set up percentages, a ratio. What's our percent of the radioactive parent to what's our percent of the stable daughter product. So percent to percent, and you can figure out an age with that using this method. So half-life, okay, that numerical value. Is the time required for 1/2 of the radioactive parent to decay into the stable daughter product, okay? Whatever that is, and that's unique for each type of isotope, okay? Could be 10,000 years, could be 3 billion years, okay, on these, but they have an exact half-life, okay? So when you see a 50% parent radioactive isotope and 50% daughter stable product, 50-50, you know that one half-life has gone by. That's sort of the definition of a half-life. Time required for half of the radioactive nuclei to decay into the stable daughter. So just by analyzing your rock specimen, you can go in and get an assay of that in the lab, and you'll get these percentages. Got this radioactive isotope versus this stable product, okay? And you can set up these different percentages, ratios. And from that, this is a nice example on this curve here, a decay curve, where here we've got the percentage of radioactive isotope remaining. The blue dots on there is our radioactive isotope, okay, the parent. Okay. The red dots on here, red or pink, can't quite tell, are the daughter, the stable daughter product. That's what it's going to decay into, stable daughter product. And so we're looking at ratios. So right up here, we have 100% of the radioactive parent isotope, 100%. So no half-life has gone by. When we see 50% parent and 50% daughter, okay, that's our definition of a half-life. So this one right here, we've got 50 atoms of the parent and 50 atoms of the daughter product, okay, 50-50. 1/2 of 100, okay, of the parent. That is one half-life. And you come down here, and that's the number of half-life. One half-life has gone by. However many years is associated with a half-life for that particular isotope. Okay. Then we continue on. Now we're here. That 50%, that's the parent. And we go through another half-life. We're going to half that. So 50 divided by 2, right, leaves you with 25 atoms of the parent, and now 75 of the daughter product, the stable daughter product. So now we know one more half-life went by. Okay, so 2 half-lives. If we go to 3 half-lives, we cut that parent in half again. So if it was 25, they're kind of rounding that to 13 atoms in our diagram, but that really would have been 12.5, right? Half of 25 is 12.5. They rounded it to 13, I guess, to make that easy. So 13 atoms of the parent to 87 atoms of the daughter. We know 3 half-lives went by. Okay, let's go again. So if we have that 13, let's cut it in half, right? It's really 12.5 divided by 2 would have been 6.25, but they round that to 6 in our diagram. So 6 parent to 94 daughter, okay? that lets us know that a fourth half-life went by. So by looking at the percentage of the radioactive isotope in your rock, they can determine how many half-lives have gone by. And then they do know the numerical value of those half-lives. And so, yeah, they can determine the age then of a rock, the numerical value of an age. So let's say we have a radioactive isotope and its half-life is 10,000 years. That's the number of years in one half-life. And when they analyzed it, they noticed that they had only 25% of the radioactive isotope. Only 25%. So let's see. Starting off would be 100. After one half-life, we would have had 50, okay, of the parent. Go a second half-life, and you would have the 25%. So 2 half-lives have gone by. So 2 times the 10,000 would mean that the age of the rock is 20,000 years. And so in this manner, with this method, they can put numerical values to rocks. Okay, and so radioactive aging is called absolute age dating. We're now able to put the numerical values to it. So that's a method of absolute age dating. Another one that they don't really talk about in here, but in your PowerPoints, but carbon-14. Okay, so we have, that's the radioactive isotope. Carbon-12 is like your normal one, but you can have a radioactive isotope of carbon-14. So in living organisms, as they're living, they're taking in carbon-12 and carbon-14 naturally in the atmosphere. And then when the organism dies, okay, they can no longer, get that balance between carbon-12 and carbon-14, and so the carbon-14 begins to decay into nitrogen, and so you can set up sort of a radioactivity age dating with that. But with carbon-14, the half-life's only about 5,370, something like that. So carbon-14 is really only good for very young events. So let's say trying to age date some wood in an Indian campfire, something like that. So we're not on the order of billions of years with that. Carbon-14, so it does have a good place, but be best to date the ashes, let's say, of an Indian campfire. Would be carbon-14. Another one, again, they don't have it in your PowerPoints, but dendrology, so the study of tree rings, counting of tree rings. This is actually, I've got a tree cookie somewhere here. Here it is. Where you can actually count the rings of the tree. Okay, so this is what we call a tree cookie. And it's just a slice through a tree. And you can count the rings. And so this is absolute, a form of absolute age dating. Because you can count the individual rings in the tree, the slice through it. It can actually tell us something about, oh, that may not be showing up very well. Not really. I'm not seeing those like I wanted to. Oh, maybe putting that different background on there helped. I don't know how well you're seeing that from where you are, but yeah, all these rings, okay? Rings can be counted, and it's an exact age of the tree. So this is very helpful, and it is a form of absolute age dating. And it can tell us something about the environment that the tree was growing in, the climate. Did it have a long growing season? Was it in a drought type situation? So it can tell us a lot from this dendrology, the study of tree rings. But it is a form of absolute age dating. Just did not get mentioned in our PowerPoints there. So that's a good way to age date some things. Okay, so the importance of radiometric age dating. Rocks from several localities, so I think a lot in Australia. have been dated to more than 3 billion years. And so that is helping us to understand this deep time, that the Earth has a very old and long geologic history. Okay, and so being able to age date some of these is very important, and it really does confirm this idea that geologic time is immense. It is thought by geologists and astronomers to be, Earth is thought to be about, I'm going to say between 4 and 5 billion years. Billion with a B. And it, you know, I think the astronomers go with 4.6 billion years, BY, billion years. So this idea that this calculated age of 4.6 billion years does tell us that geologic time is immense. Okay, so we've got to wrap our brains kind of around that as we're studying geology. Okay, so we want to look now at the geologic timescale, and as I mentioned before, this was constructed entirely by those relative age dating methods originally. So we only put those numerical values as we got that technology, in the 1950s of the radioactivity, the absolute age dating. Then they added some numerical values to the geologic timescale, but it was originally completely constructed by the relative age dating principles that we talked about earlier in there. But this is going to subdivide history into units. It's kind of like a calendar of the history of the Earth. But what's nice about it is that it shows you the evolution of the land right alongside the living organisms, life on our planet, which is really nice to have that because they did evolve together, living organisms right alongside the land. So yeah, created using relative age dating. So it didn't have the numerical values, but it said this happened first. This was the oldest event. This was a little younger. This is a little younger. And so at the very top of the geologic timescale is your most recent events. Way down at the bottom, your oldest events. And so that has a lot to do with superposition, right? The lowest and oldest event is at the bottom of your rock layer. Well, it's at the bottom of our geologic timescale as well. So that idea of superposition is a theme in our geologic timescale. Yeah, so the structure of it, the eon is the greatest expansive time. So it's almost like chapters in a book kind of thing, with ending of a chapter, some traumatic type of event happened. A lot of them end with a mass type of extinction that happened in it. But an eon is your greatest expanse, okay? This kind of shows the trends of the life and that sort of thing. And then here's one eon. The Phanerozoic is the visible life. And so much of what we know about the geologic timescale is in this Phanerozoic eon. Okay, it's the shorter one because visible life was, was kind of hard to come by because of the lack of hard parts, right, and getting the fossils. But it's the most recent eon, and it began about 540 million years ago. So just a fraction of this 4.6 billion year geologic history, right? 540 million years. But that's our most recent, that's the one we know the most about. But that's called the Phanerozoic. As you keep going back older and older, the Proterozoic, the Archean, and the Hadean is the oldest. Now these three right here, Proterozoic, Archean, and Hadean, get lumped together in what we call the Precambrian eon. We kind of put those three together. There's not a lot that we know about that, so there's not a lot of different events in there because it is so old and we did not have good fossils during this time. So, you know, about 88%, 87 to 88%, okay, that Precambrian eon, okay, is represented by that time span. All of these kind of encompassed, called Precambrian. So few fossils in the Precambrian because those animals lacked hard parts, as we'll see. There were, you know, single-celled organisms, multicellular organisms, but soft body kind of things, soft. So we didn't get good fossils from it. Okay. All right, Precambrian, like I said, kind of lumped together all of that before the Paleozoic, those other three, Proterozoic and through Hadean. Okay. Then, those were eons, two broad eons. Then the eras, okay, of the Phanerozoic, because that's going to be the one that we know the most about. And so they've got those subdivided into some chapters here. Cenozoic would be the most recent, so that would be towards the top of the geologic time scale. Mesozoic, middle life, Mesozoic, middle. And Paleo. Paleo means ancient. Remember paleontology? Ancient life. Okay, Paleozoic. So most recent to the oldest within our Paleozoic. Phanerozoic eon. Okay. All right. So eras get subdivided then into periods. So again, now we got some little chapters within each one of those eras. Okay. And then they're going to show us pretty soon. But the Precambrian, like I mentioned, about 4 billion years of it, right? So if we're 4.6 billion years and almost that 0.6, 540 million years, you know, before that, it's all Precambrian. About 88% of our time, okay, is in the Precambrian. And it doesn't really get divided up too much. Again, we don't know that in enough detail, okay, to go into greater detail. The first abundant fossil evidence doesn't come along until the beginning of the Cambrian, okay? And so we're just beginning to get into organisms with hard parts in them. So here's all that Precambrian. It's actually, you know, quite a large expanse of time. Yeah, most of that 4 billion years is set up in the Precambrian. So that, you know, it's a much larger time expanse, but they're just blocking it all right there. First multi-celled organisms in the Precambrian are the best that we can come up with in there. So that starts 540 million years, okay? The beginning of the Cambrian that they talked about. This is all the Paleozoic, okay? So Cambrian through Permian. You will not have to remember all of these, but there's a few that you might want to keep in mind as we go through. We'll look at each one of those. Here's the Mesozoic, okay? Triassic, Jurassic, Cretaceous, so Jurassic Park, you know, dinosaurs, time in there. And Cenozoic was the recent, and they block that into tertiary and quaternary, and then they have these little epochs, okay? The most recent epoch is the Holocene. That's when humans come into play. So here we are, way at the top, humans develop. So most recent with the humans. So that in a nutshell is the geological timescale. So we'll take it, I think they're going to take it and have you look at each one. So starting in the Paleozoic time, okay, that era, and then we're blocking that into these periods. And so right down here, first organisms with shells, okay, hard parts. So we're getting some good fossils out of this. That's Cambrian. So it's also known, so what's going on with the living organisms, the age of the invertebrates. Invertebrates didn't have a backbone, okay? So the trilobites become dominant during this time. Scurrying along the ocean floor there. So all organisms are within the ocean, right? So life evolved in the ocean. So nothing on land yet, okay? Trilobites are dominant. We got Ordovician, and then the first fishes come along, okay? The first fishes. Here we are, the age of the fishes. first land plants. So now we're starting to get organisms being able to get onto land, but it was plants first, okay? Fishes are dominant. Our first insect fossils are coming along, so that's Silurian and Devonian. This one here, the Mississippian and the Pennsylvanian, sometimes are lumped together as a Carboniferous. So this is when a lot of the coal swamps, the coal beds were being deposited in there. So age of amphibians. So the amphibians are the abundant organisms. Large coal swamps are going down. First reptiles, okay? At the end of the Paleozoic, we ended, kind of like we're ending that chapter, by a mass extinction. My trilobites, they're not mine, but my little favorite fossil, the trilobites, go extinct. A mass extinction. Of course, other marine organisms, about 90% of the marine organisms go extinct, never to come back. So there was something that probably plate tectonics, okay, could be happening. Climate, their climate changed, and they were no longer able to adapt, and so extinction occurred. So they're never coming back. But that happened at the end of the Permian, or the end of the Paleozoic, during the Permian time period. So the Great Permian Dying, they called that mass extinction in there. That was a Paleozoic. And then the Mesozoic, so in the Triassic, dinosaurs are becoming dominant, and they call this the age of the reptiles. They're doing very well during this time. Our first birds are coming along, first flowering plants. And here, notice at the end, so here's Cretaceous, Jurassic, Cretaceous. At the end of the Mesozoic, here again, end of that chapter, by another mass extinction. And so 66 million years ago, extinction of the dinosaurs, but they weren't the only one. Many other organisms. Mass extinction happened about 65, 66 million years ago at the end of the Mesozoic. So another mass extinction happened at the end of that one. And then the Cenozoic, okay? Paleocene, Eocene, Oligocene, Miocene, Pliocene, the Pleistocene, right? The Ice Age there, Holocene, okay. So age of the mammals. So after the dinosaurs went extinct, we get this age of the mammals. So they found a niche and they did fine and developed, and then way at the top, humans developed. So we're just like the really latecomers in this geologic time expanse, okay, the time scale in there. So that's kind of the way that the geologic time scale was put together, okay. That ends that book work anyway, but we are going to take a walk through Arkansas's geologic past, okay, as I mentioned before. And so that little handout that I gave you that had all those various figures on it will become important for you to kind of have that handy as we talk about these. Pictures that should be matching your figures, and your figure may have a different figure number, okay? If this would be your figure 1 in your handout, right? So this is the handout, and I'm calling that figure 1, late Precambrian, okay? So towards the end of that Precambrian, 900 million years ago, and that's this picture. Here, it might show up a little better than that one. But Arkansas was underwater, okay? So here's Arkansas. This is all underwater, okay? Missouri had some volcanoes where there was a little bit of land up above the surface, right? Coming up above the surface there, but underwater. And the organism during this time were stromatolites. Stromatolites, these little algae, okay, little algae organisms that you know, they kind of secrete, and then sediment gets in on them, kind of like an algae, kind of a algae flat sort of thing. But they got put into the rock record with these stromatolites, we call those. There's a picture of it. We'll put them side by side, where they've been kind of, looks like a head of cabbage that's been kind of cut off there, with the little rings of stromatolite, layer after layer after layer. And then, so these are some of the earliest organisms, fossil organisms, are the stromatolites. Fossilized microfossil kind of bacteria, blue-green algae. The stromatolites were prolific during this time. Okay, and then figure 2 for you, we've got that early Paleozoic, so about 600 million years ago for our figure 2 in our handout. Of course, this one's numbered a little different. Lots of figures in here. So during this time, we get a rifting of Arkansas. And a pulling apart, so a rifting. Okay. 600 million years ago. And so if you remember, we talked about the New Madrid fault zone, the earthquakes. A lot of that's up there in Missouri. But it does come a little ways into Arkansas as well. But that's when this sort of ancient rifting began to occur. And so that's why we have that kind of a rift zone, the New Madrid fault zone here. It was occurring about 600 million years ago, an ancient kind of rifting. So a little bit of pulling apart as, of course, the plates were moving, plate tectonics were moving, creating a little bit of a rift. And they're still underwater. Arkansas is still underwater. This is the age of the invertebrates during this time. Almost like a Cambrian kind of explosion in here, where you got a great diversification of living organisms. So my trilobites, right? They're not mine. But the trilobites and the brachiopods, we saw those trilobites, but let me find some brachiopods for you. Are about 400 million years. And I had my trilobites somewhere in there. Here they are. So here's our brachiopods, around kind of in that time frame. These guys were doing very, very well. Nice picture of them. The feeding organs in there, pedicle. This little card kind of talks about some of them. In there, sinuous, kind of fleshy stalk, but a shell, okay, in that. And then this was my little trilobites. A little tiny one there. These are the trilobites. These organisms were doing extremely well during this time. In yes, that second figure. Okay. Invertebrates, we call these. They don't have a backbone. Okay. And so they were doing really good during that time. Our figure 3, okay, middle Paleozoic. So we're getting along about 450 million years on this one. Okay, this is an interesting one. This is showing that Arkansas is underwater, okay, and is more of sort of a ocean environment where we have more of a continental type of a shelf to the north of Arkansas. Here you're starting to see some little islands that are getting above the water. So a little more shallow in this northern Arkansas region. And so shelf, they call that, like a continental shelf area, a little more shallow. And then here we have a slope, so it kind of drops off on the ocean floor as a slope, okay, continental slope. And then here, southern Arkansas is in sort of a deep ocean basin region, so it's a much deeper ocean kind of environment in southern Arkansas. Again, this is about 450 million years ago, getting to middle Paleozoic in here. Okay, sort of a trough down in through there. On Mississippi River yet. Okay, so age of the fishes. This would have been where, I don't know if I brought that, the Ruggos coral would have been coming from that. In that ocean, a little more shallow environment, water environment, where you could get the corals, the Ruggos corals forming. And so, yes, again, solitary and colonial. I think I do have it. Here we go. Here's my coral. Some horn coral right there. This one from northern Arkansas. Down a bit. They've got this one dated at 375 million years. So this one, 375 million years. Okay. This is just a little card about the corals there. Soliterates. There's that Ruggos horn coral. Singular solitary type corals, but I've also got in here colonial or colony type coral as well. But again, northern Arkansas, we see this in the rock, bedrock. But yeah, all of these would be a little coral organism, so a colony of them. But that's what's occurring. So we've got a warm continental shelf type ocean type environment in Arkansas, okay, the Ozark Plateau kind of region up in there, and southern Arkansas down in the deep ocean basin type of a setting. Okay. This is the age of the fishes, right, during this time. Okay. Let's go to our figure 4. This is going to be late Paleozoic, so 350 million years ago. If I can find it. Here it is. Yeah, 350 million years ago. So here, North America, okay, so yeah, 350 million years ago, in that one, Pennsylvanian period. Notice up here towards the north, because we kind of had the shallow water in that figure before. Now we're actually starting to get a river type of a system, a delta kind of forming here. Still this part of Arkansas underwater, still. But we're getting rivers bringing a lot of that sand and gravel that builds up the Ozark Plateau in there, right? The rock and the bedrock that we see, the shales and the sandstones that we see. So rivers kind of bringing all of that material. This is where Pangea is still assembling. So we're having North America, South America, and Africa all kind of coming together. So we're assembling Pangea at this point, 350 million years ago for this one. And really wrinkling up, okay, in the middle kind of part of Arkansas. And you're seeing here, we call these sea fans, where this is underwater, but it's still bringing that sediment kind of down in here. And these are submarine hills towards the bottom of Arkansas, southern Arkansas. Submarine, so under the water at this time. no living organisms on land at this time. Amphibians are beginning to appear in the middle of the Paleozoic, okay? Arkansas was located a little closer to the equator. Like I said, as Pangea is trying to come together, the land is moving, the plates are moving, and it actually put Arkansas a little closer to the equator. So climate can change, okay? And so as you get the plate motion, you're moving the lands to different latitudes. It can change your climates, and you can get real problems for the organisms living in there. So these mass extinctions can be explained from climate changes due to plate tectonics, because it's moving them to latitudes that they're not used to. Okay, so we've got some first amphibians kind of appearing. You do get sort of that transitionary lungfish in there where it can gulp air for short periods of time. It's got more, its fins are starting to be a little more sturdy, where it can kind of go from a little pool to another little pool as it was able to adapt a little bit. And so that's sort of the link between our fish and our amphibians, that some of the features that actually help them to live on land. Okay, so another thing we were seeing at this time were those large coal swamps could be created during this time. Okay, that's our figure 4. And then figure 5. Here we're getting that Ozark Dome, okay, to come up. So here's that Ozark Dome, originating there in Missouri. Just stay put. Okay, so still Pangea assembling, South America squeezing in, Africa squeezing in. Here's where we're getting severe deformation in the Ouachita Mountain region. So those reversed thrust faults, right? Those reverse dip slip faults, the anticline, syncline, really a lot of compression happening during this time. This one's our figure 5. So we're talking about 250 million years ago. It straddles the Paleozoic and the Mesozoic in here. But yeah, towards the end of the Paleozoic, we are getting the Ouachita Mountains to that dome to rise up, the Ozark Dome, and the Ouachita Mountains are getting set as well, getting really deformed in that region. So we get the Ozark Dome mountains out of water, Ouachita Mountains starting to get really wrinkled up in there as well. And a lot of that sediment is going to wash its way down to southern Arkansas, so sort of Gulf coastal-like plain, the southern part of Arkansas. So a lot of that's getting washed down, running off from the Ouachita mountain region. Mollusks were a large group in this one, so the cephalopods and the nautilus, ocean-type organisms. If I can find very beautiful, there's a nautilus, and the cephalopods, you can see the little sutures on the cephalopod, so little organisms, right? And as they grew, they would create a little chamber, and another little layer, and another little layer, and so as they grew, they would have a little chamber with air, a little pocket of air, so it could keep it buoyant and it could move somewhat. Here's a nautilus, where that's a much larger one, where you'd have the organism little tentacles out here, and then it would kind of propel itself along. So here's a nautilus. I've got one that's cut open here. You can see inside of that the chambers. So as it grew, right, secreted a little layer and another little layer and another one as the organism would grow. So cephalopods and these nautilus were very prolific organisms at this time. Ozark Mountains getting uplifted on figure 5 there. Okay, so figure 6 then, we're reaching about 200 million years ago. So at that point, Pangea has been all assembled and it's beginning to move apart now, pull apart again. Pangea is. Let's see, this needs 6. Go forward a little bit. There it is. So now, instead of coming together and all that compression, now we're getting an extensional type of a force, pulling apart, tension, with the separation then of Pangea, right? So pulling apart, and as you do the pulling apart, if you remember, I had my little fault blocks that I was showing you and I pulled apart, the center part would drop down. That was called a graben. And so, yeah, you're getting a graben down in through here as well. And so there's Arkansas that's getting a little bit of that. Our Arkansas right here, kind of towards the bottom in there. Ouachita Mountains through here. Got the Ozark Dome formed towards the top there. And yeah, so Pangea begins to kind of pull apart at this one, and you get that graben down in there. This is the age of the reptiles, also known as the age of the dinosaurs, too. And so there were actually, dinosaurs weren't just large reptiles. There were structural differences between them. So, for example, in their limbs, a crocodile or an alligator or something, they walk like this, on all fours, but like this. Dinosaurs had their limbs up underneath them and would walk like this. An alligator or a crocodile, their tails drag on the ground. But for a dinosaur, okay, my old dinosaur will stay together. Their tails were up off of the ground, okay, walking on all fours. So definite structural differences between reptiles and dinosaurs. They weren't just giant lizards kind of thing. They were not. Even though their name says it translates to terrible lizard, there were structural differences between the reptiles and the dinosaurs. But yeah, this is kind of the age of the dinosaurs, about 200 million years ago. For your figure 6 in there, early kind of Mesozoic, you were getting the Pangea to rift apart in there. So yeah, dinosaurs. Definitely doing a good job there. Let me go back to, there was a cute little picture of a dinosaur. Oh, let's see. Here he is during this time frame. This is in reference to the dinosaur footprints that we had in southwest Arkansas during this time. He's wearing a little Arkansas, and he's just walking along the beachy area, leaving behind his footprints that we later discovered, right? So that was really cute picture in there. But yeah, so that was our figure 6. Figure 7 is getting us towards about 65 million years ago. So now we're into the Mesozoic and straddling to the Cenozoic on this one. Okay, so northern Arkansas is out of water, we could see, and still, okay, southern Arkansas is still underwater. It's like the Gulf of Mexico, right, all the way up here in Arkansas. And so that's where we're getting that stratigraphic province of the Gulf coastal plains, okay, because of the gravels and the sands that we're getting that pretty much were eroding off of the Ouachita Mountains and making their way down to this region. But this was underwater still, southern Arkansas, about 65 million years ago. We were getting our gypsum deposits. So I did mention that southwest kind of corner there where the dinosaurs' footprints were. The gypsum deposits, again, those are evaporite deposits. So they're evaporating out of kind of that seawater, okay? Has the gypsum in it, the calcium sulfate in it. So yes, that time frame, southern part of Arkansas is still underwater in our figure 7. Getting the Mississippi embayment, so we're starting to get where the Mississippi River would be flowing. As far as living organisms, one of the earliest flowering plants was the magnolia tree. So a lot of magnolia trees in our area, but yeah, that's sort of the time that we were getting the flowering type of plants, the angiosperm type of plants were evolving. And again, towards the end of the Mesozoic, this is another, truncated with another mass extinction where the dinosaurs, including other organisms as well, went extinct, okay, at the end of the Mesozoic. And so their best belief, it could have been a perfect storm of several things, but the ongoing kind of latest, most accepted theory on that is that the Earth was hit by a meteorite. They have a lot of geologic evidence for that. That created, a bunch of dust that blocked out the sunlight for an extended period of time. That caused a mass extinction. Some other ideas, and again, it might be a combination. We had more volcanism going on again, putting up a lot of ash, and that together, those things would definitely cause a mass extinction. So a prolonged period of time. Okay. And then let's see. Still in this one, the Cenozoic. So kind of on the Cenozoic side, mammals come out as the dominant organisms. The age of the mammals in the Cenozoic time period. The horse kind of co-evolved. I think I had, yeah, I do have some horse teeth, okay, where one is from a couple of these here. An oreodont, we call that. Well, you can see all of that. An oreodont, okay. This was a small, this is about 30 million years ago. Small little, kind of a shrub-eating organism that underwent structural changes to the horse, kind of co-evolved with the horse. Here's the horse teeth. A small kind of goat-like animal there 40 million years ago. And then here's the horse teeth. And so the horse pretty much evolved along with the grasses, the oats and the barleys and things like that. So there was definitely a structural change with the teeth from where you were eating, from shrubs and the woody parts versus the grasses. The horse teeth are just going to continue to grow and be ground down, so more of a grinding of grasses. But the horse kind of co-evolved with the grasses as life was proliferating. So that's sort of in the figure 7 realm. Okay. End of Mesozoic, beginning of Cenozoic was that time frame. And then figure 8, your figure 8, we're beginning to get towards about the 25,000 years. So now we're not even millions, we're 25,000 years towards kind of the end of Cenozoic. 25,000 years ago in an epoch called the Pleistocene. That's our ice age, so the ice age. Now, glaciation, so you're seeing ice, okay. encroachment of the glaciers, spreading out, expanding out again, climate changed enough to where now we were getting more glaciers up on the land. Never got here to Arkansas. The glaciers never made it this far. But we did get this ridge that formed, Crowley's Ridge here, from glaciers that will really erode and powder up your rock, almost like rock flour. And then that light rock flour will get picked up by the wind, and it got deposited in Crowley's Ridge. We call it Loess, L-O-E-S-S. That built up that ridge there for Crowley's Ridge. So the ice didn't make it here, but some of the effects of the ice, that rock flour that the wind picked up, we did get Crowley's Ridge in there. But yeah, so Ice Age, think of the Pleistocene epoch in there. We are out of the water down here, kind of towards the bottom of Arkansas. We're finally above the water at this point. But glaciation never really covered Arkansas. Of course, you're getting towards the end of the Cenozoic, where the earliest fossils of Homo sapiens, so humans, were found in the East African Rift Valley. A lot of paleontology goes on there, but we've talked about the East African Rift Valley several times in here, significant regions for that. But earliest fossils of human descent, the Homo sapien, were found in the East African Rift Valley. So of course, humans and dinosaurs never roamed the earth at the same time. A caveman would never have seen a dinosaur. So yeah, those movies and those cartoons, the Flintstones notably, their pet dinosaur, Dino the dinosaur, would have never happened, right? So humans and dinosaurs never roamed the earth at the same time. So yeah, so that's that eighth figure in there. And so I want to take one last look here at the rock beds, the type of rocks that we do see here in Arkansas. So I have this geologic map of Arkansas, kind of color coded, and you may not be able to see that too well there, but of which of these different eras we do see. Now, Precambrian rocks are not seen or visible in Arkansas. That's like a very old event, so those would be buried very, very deep in the Earth's crust. But looking over on the eastern kind of portion of it, with the yellows and the oranges in there, these are more recent. So the Quaternary and the Tertiary, so with those little sub-units of the Cenozoic, so more recent that we're seeing over here. The gravels and the sands that we see coming from the Mississippi River and all that. So those are recent deposits in there. We do have some Cretaceous, so which would be Mesozoic that we've mentioned. That's here in the green, right here. In southwest Arkansas, so if you wanted to go see some Mesozoic time frame of the rock in the bedrock here in Arkansas, you'd want to go to southwest Arkansas. Recall the gypsum deposits and those dinosaur footprints that are no longer, but where they did study those and got the casts and the molds made of that. But yeah, right there in southwest Arkansas, okay, all that green there, you would see some Mesozoic rock in the bedrock there. Okay, so Paleozoic, you would basically, it's this kind of a purpley color. So Pennsylvanian, Mississippian, Silurian, Ordovician, all of these are Paleozoic. So pretty much the western part of Arkansas. Okay, you're going to see Paleozoic time period rocks from there. Okay, various ages there. But that's in our bedrock, and so no Precambrian are visible though. So that kind of is why we've set up kind of an explanation of why we have the geographic provinces, stratigraphic provinces that we have of the Ozark Mountains, the Arkansas River Valley, the Ouachita Mountains, the Gulf Coastal Plains, why we call them what we call them. Over here, Mississippi River Alluvial Plain, so all that's being washed, the gravels and sands coming from the Mississippi River. And then that Crowley's Ridge right up in there. That actually was from the Pleistocene, the glacial age, where glaciers were advancing. They never got to Arkansas. But that rock flour that got ground up by the glaciers, and the wind blew it, and there we have our Crowley's Ridge. And so that's sort of an explanation of why we see what we see in the bedrock, and sort of explanation of your stratigraphic map of Arkansas. And so I hope you enjoyed that little stroll back in time, geologic time, through Arkansas. So that's going to conclude the course. And so I certainly enjoyed bringing you the material. I hope you've enjoyed it as well. And I just hope that you get a better understanding of our Earth and its operation, but also that, very importantly, that you are very much a part of geology. Okay. Thank you so much.